All right, today, lesson 1-6, is that right? We're doing domain and range in real worlds. This is a follow-up. It's a part 2 to the last lesson. Davey, make sure you're with me here. It's a follow-up to last lesson. We're still doing domain and range. What's different today is we're going to look at real-world problems, meaning they're going to be like stories. And we're going to figure out what the domain and range is from a story rather than just a graph, like we did last class, okay? So you can look through this. That's what we're learning to do. We're learning to identify the domain and range of linear functions in real-world problems today. That's what we're doing today, okay? So with that, let's get started. Come on now. Board fell asleep on me. So when we do real-world problems, the first thing we have to figure out is, that's too large, let me shrink this down. The first thing we have to figure out is what's the independent and dependent quantity, meaning what depends on what. So in a real-world problem, you have to figure out which is your x and which is your y, because as we talked about last class, when we do domain and range, we say Dr. what? Dr. XY. In the real-world problems, they won't tell you, hey, this is my domain, this is my range. We have to figure that out. So we have to figure out what is x and what is y so that we can then say what the domain and the range is, okay? So sometimes that's a little tricky. So here's what we're going to learn. The x is called the independent quantity. Go down over here and put, this is the letter x. Go ahead and put that on your note. The dependent quantity is what we call the letter y. Now what this means is that the y depends on the x. So when we look at these problems, we're going to be talking about what depends on what. So here we go. This is just an idea. Let's look at this first situation right here. Have you ever planned a party? You may have purchased ice, gone grocery shopping, selected music, made food, or even cleaned in preparation. Many times, these tasks depend on one another. There's the word, depend. On another task being done first. So, depend is the word. See how this says dependent? The y is going to depend on the x. For instance, could you make your food before you went grocery shopping? Let me ask that again. Could you make your food for the party before you go grocery shopping? No. So the food you make would be dependent upon the groceries you bought. Does that make sense? In this situation, the food you make would be your y because it depended on the groceries you bought, which would be called the x. The x would be the groceries you bought. The y would be the food you made. For example, if you went and bought a bunch of chips, that would be your x. Would you then make pizza? Y. Would you use chips to make pizza? No. No. So that would be, what I'm trying to say is the y, the food you make, depends on the food you bought. If you bought chips, maybe you're making nachos. Maybe you're making a salsa for a dip or something like that. I don't know. But the point is, you have to think about what depends on what. Follow? All right. With that, let's go through here. What we're going to do is circle the independent. That means the thing that happens first. And then we'll underline the dependent. The dependent is the one that depends on the first. So we're going to circle the independent and underline the dependent in each one. And then we'll come back and do number 2. Okay, so first, the number of movie tickets purchased and the total cost. What depends on what? Does the number of tickets purchased depend on what the cost was? Or does the cost depend on how many tickets you're purchasing? Which way is it? The cost depends on the movie ticket. So what would you do first? What would happen first in order if you're going to the movies? What would you say first? Would you say, hey, here's $20? Or would you say, I want this many tickets? What happens first? You want this many tickets, so we circle that up. The movie tickets purchased, circle that up. That's what happens first. And so what depends upon the movie tickets purchased? The cost. You underline that. So this depends on that. I'm going to put that word depends so you get used to it. That's why this is dependent. This is independent. That means it doesn't matter what this one is. your movie tickets purchased determines the cost. Okay, let's go to the next one. The number of eggs used and the number of cakes baked. The number of eggs used and the number of cakes baked. So here's a cooking one. What comes first? Do you use eggs first or do you bake cakes first?
Eggs.
Eggs first to make the batter, and then you make cake from that batter. Very good. So we underline we circle the first one, number of eggs used, and then we underline the dependent, number of cakes baked. I'm going to go ahead and do this, arrow back, and I'm going to say depends. Meaning this depends on that. That's what my notes are indicating. Okay, how about the next one? The number of lunches served at school and the number of students in attendance. If we want to know how many kids were at school that day, do we say how many meals were prepared? Or if you want to know how many meals prepared, would you ask how many kids are in attendance? Kids are in attendance comes first. Meals come last. Okay, good. So we circle number of students in attendance. We underline number of lunches served. So this depends on that. So this is what I mean about real world problems. We have to figure out what's X and Y. Hey, Lewis, make sure you're not on that right now. Here we go. How about the next one? The number of hours driven and the number of miles to a vacation destination. The number of hours driven and the number of miles to a vacation destination. Does the number of miles to the vacation destination depend on how many hours you drove, or does how many hours you drove depend on how far you had to go to get there?
Miles to the vacation destination depends on how many miles you drive.
Okay, that's not the question. Wait, I don't think the number of hours driven and the number of miles to the vacation destination. Maybe that's what you said. I don't know. I think I heard something wrong. Say it again. Which one's independent? Which one depends on what? Is it the number of miles depends on how many hours? Or does how many hours depend on how many miles away it is? Hey, I want to hear more than Contravian here, and I think maybe Caitlin's spoke up, but I need more people participating here. What do you think?
The number.
Davian, how about you? I'll come back to you, Contravian. Which ones? Is the number of hours you drive dependent on the number of miles you have to drive? Is the number of hours depending on how many miles it is away? Or is the number of miles away depending on how many hours? Miles is dependent or independent? What are you saying? Miles is what? Okay, so you're saying the number of miles depends on how many hours? Hey, Danny. Come on now. Rosario, what do you think? Would be which one? The first thing or the second? The first. Okay, I agree with Rosario. The number of miles away would determine how long it takes to get there. For example, if I told you, hey, we're going to travel 5 hours away, does that mean it's 100 miles? Does that mean it's 200 miles? Now, you don't know. But if I said it's 200 miles away, could you then figure out how long it'll probably take to get there? Yeah, so the miles come first. So let's circle up the number of miles to a vacation destination. That's our independent. The number of hours driven is the dependent. The number of hours depends on how many miles away it is. All right, Danny, I'm going to give this one, the last one to you here. The number of gallons of water in the swimming pool and the number of minutes a swimming pool has been filled with water. So the number of gallons of water that are in a swimming pool and the number of minutes the swimming pool has been filled with water. To make this more clear, like with a water hose. You're holding a water hose. Which one comes first? Is it the number of gallons of water in the swimming pool? Or is it the number of minutes the swimming pool has been filled with water? from a person holding the hose? What would come first? Danny, I was gonna have you. What do you think? What comes first? That's right. You're holding a hose. The number of minutes you've been holding that water hose would determine how many gallons of water are actually in the swimming pool. Does that make sense? So the independent is the number of minutes. The swimming pool has been filled with water. The number of gallons of water, that's the dependent. This depends on that. Now, number 2 says describe how you can determine which quantity is independent and which quantity is dependent in any problem situation. What we're doing, and that I kept trying to write in here, is this word depends. How you do it is you try to figure out which one depends on the other. So, which one comes first is another strategy. Which one would have to come first? That would be independent. But the other way is to say, okay, then the second would depend on the first. And that's what I did here as the second thing. Okay, so now with that, here are some usual continuous things. Continuous things, so we're going back to continuous and discrete. I did not do that on this one. What I mean is, remember a few classes ago, continuous means the graph is connected. Discrete means the graph is dotted. We talked about that last class. Said a few classes ago, it was last class. So what we're doing on the next page is we're going to talk about in these situations, we have to know, is something discrete, meaning dotted, or is something continuous, like this? The easiest way to think about it is if you're going to ask yourself, continuous means it's measurable, like you measure it somehow. Discrete means you count it. So, for example, let me come back over here. The number of movie tickets purchased. If Lewis told us he went to the movies and we wanted to know how many tickets he purchased, would you pull out a measuring tape and measure all the tickets out? Would you pull out like something you would scoop flour or sugar with and fill them in there to see how much? Would you measure it that way? Or would you count the movie tickets? How would you do it? Count. This situation right here would be discrete. Up here on this one, put that this is discrete off to the side. This is discrete. Discrete, remember, means dotted. My stuff froze on me again. Okay, put that this is discrete. I gotta wait for mine to wake up. Discrete. I don't know what's going on with it. There we go. Discrete. That just means my situation would have a dotted graph. Oh man, my stuff's going so slow. What's going on? Okay, how about the next one? The number of eggs used and the number of cakes baked. If you were going to talk about eggs, would you measure eggs or would you count eggs? You would. I'll give you a hint. It says number here. Do we measure numbers or do we count numbers?
Count.
Count. This would be counting. You would measure batter. Like once it's all mixed, you would measure the batter, but that's not what it says. It says the number of eggs used. You wouldn't measure the eggs used. You would count. I used 8 eggs. I used 9 eggs. I used 10 eggs. So that's how that would work. Okay. So this one would, number 2 would also be discrete, which means it would be dotted. Okay, how about this? The number of lunches served and the number of students in attendance. Would you count students? Would you count meals? Or would you measure students? Measure meals. What would you do here?
Count.
You would count. This would also be discrete. You'll notice many problems in the real world are often discrete. Not all, but many are. Okay, the number of hours driven and the number of miles to a vacation. Now this one's a little tricky because I just said the word number, but if you were looking for the miles and you were looking at a map, this is weird for y'all because now GPS, you just type it in and it tells you. But old school people, people like me who are old and bald, when we were kids, what did we do on a map? Did we count miles or would we measure? You would measure. This would be measurable. The number of hours driven. So how long would you drive? You would actually Time is a kind of like a measurement. It's a little bit different. Don't think of a tape measure, but you would measure on a clock how many times it's gone around the clock, um, so on. So this would be measurable, and so this would you call continuous. This one would be continuous. What's tricky is they say the number. If it just said the hours driven, um, that would make more sense. And the same thing here. Instead of the number of minutes the swimming pool, they said how many minutes the swimming pool has been filled. That's the same thing here. If you were talking about pouring water, gallons itself is a unit of. Is gallons a unit of counting, or is that a unit of measurement? What is gallons? That's a measurement. Yeah, this one's also measurement, and so this would be continuous as well. You want to write this. This would also be continuous. So what's the difference? What it means is if you're continuous, you can have like a half or whatever. Like is it possible to fill a pool for 1.5 minutes? Could you fill a pool with water for 1.5 minutes? Yes. That's what continuous means is that you can have decimals. That's what continuous means, you can have decimals. And that's why I always say it's measurable in that sense. Discrete means you can't have half. Can you have 5.5 people? What if they're really short? Still don't count as a half a person? Okay, what if they don't have all their arms? Still a full person. So those are discrete, cannot have decimals. Continuous is when you can have halves and stuff like that. Okay, so that's why we say like when you're filling water, could you fill it for 1.5 minutes? Or would it have to be, hey, I filled it for 1 minute. Now I filled it for 2 minutes. Could you have half a minute? That's why it's continuous. Okay. Could you have half of a movie ticket? No. No, you either have a movie ticket or you don't have a movie ticket. But no one sells you half a movie ticket. Make sense? They don't do half price because it's half a ticket. It's half price maybe because of the time, but they don't do half price because of it's half a ticket. Okay, so remember this chart right here? We looked at this last time. We're going to use these symbols, the same thing. You can look back to this at any point in time to help you out. If it's discrete, we're going to use these symbols to list our values. If it's continuous, we use these less than, greater than symbols for domain and range, all right? Today, I'm also going to try to use some word, I'm going to write it out in words, okay? So let's look at example 1 here. It says Susie sells cookies for $1.50 each and paid $5 for supplies. She bakes a total of 10 cookies. This situation can be modeled by this function, where x represents the number of cookies and f of x is her profit. What I wanted you to know is the independent is x. So remember how we were just doing independent, dependent? The number of cookies, I want y'all to mark that. So let's mark it the same way. Let's circle this. X represents the number of cookies. F of x is your y. If you did not know, in math, we say y equals f of x. Y value is the f of x. So when it says f of x, that's the y's. F of x represents her profit. So underline that. Her profit depends on the number of cookies sold. Now I'm going to give you a big key for today. Are you ready? Hey, are you ready? Wake up, David. Are you ready? Danny, are you ready? No. Let's try this again. David, are you ready? No, that doesn't work. Are you ready? Yes, sir. There we go. Danny, are you ready? All right. Here's a huge shortcut for you. You ready? When you see, are y'all ready?
Yes.
Okay. This word each, circle this word each. When you see an each, that's going to become your X in a real world problem. How can I prove it to you? Look at this problem. You see how this says $1.50 each? Look in the equation. You see this 1.5? That's the $1.50. What's attached to the $1.50? X. When you see an each, that's going to be your X. All right. So here we go. What is the independent variable? Well, we already marked it. What is the independent variable? X, which is the number of cookies sold. X, which represents the number of cookies sold. Number of cookies sold. Okay, now we need to find out, is it continuous or discrete? Remember, this means connected, this means dotted. We need to think about the word for today for real world. Continuous means it's measurable. Discrete means you would count them, countable. You would count them. Okay, if you're talking about the number of cookies sold, would you measure how many cookies you sold? Or would you count how many cookies you sold? Count. So that means this is discrete. Discrete. So now when we talk about domain, remember how we use Dr. XY? Dr. XY. Domain is what the question is. Domain means, what are we talking about? Which letter? X. Okay. What's the smallest number of cookies you can sell? We go from smallest to largest. In this problem, what's the smallest number of cookies you could ever sell? 1. Okay, good. Could we sell -5 cookies? Why not?
It's not a number.
It is a number, but why could you not sell -5 cookies? Yeah.
Real world. Well, I can't say it.
You're right. It's a real world problem. We talked about this. You can't have negatives. In most real world problems, you cannot have negatives. Could you sell -5 cookies? No. So what are we going to say is the smallest number of cookies you could ever sell?
1.
But what if you go broke? What would you think that means if you go broke? Okay, but what would that mean about selling your cookies if you're going broke? Why would someone go broke? Is it because they were only selling 1 cookie? What if you went fishing? What's the smallest number of fish you could ever catch? 0. There it is. 0. What if you're selling cookies? What's the smallest number you might ever sell? 0. The smallest we would ever sell is 0. So when it's discrete, if you remember, you use these symbols and you would say 0 and then you comma. Now, how many else could you sell? Could I sell 0.5 cookies? No. What would be the next smallest you could sell? 1. And the next smallest? 2. And I'm going to go dot, dot, dot. Are you okay if I do that? What does that mean? I'm skipping numbers. Now, could we sell infinite amount? Answer in this problem is no. I could not sell infinite in this problem. Look in this problem. It tells us how many could we actually sell? What's the most amount of cookies we could ever sell? 10. Why?
Should don't be baked into.
We only baked 10 cookies. Could you sell more than 10 then? No. So I'm going to go dot, 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 and then I'll do comma 9, comma 10, like that. That just means I skipped some numbers. Remember, if it's discrete, you write it like this. Okay, how about range? What does range mean again? Y values. So now we're talking about the Y values. So if we sold 0 cookies, what you need to do is plug that in right here to this equation. Actually, you have your computers open. I'm going to show you how you can do this. Go to your computer, open up Desmos. Let's type in this equation. This will be good practice for us. Type in this equation, f of x equals 1.5x minus 5. Remember, use this star version. If you go on your Algebra 1, go to classwork, and you'll see it right there at the top. Open up this star version. Okay, now that you have it graphed, I want you to hit this wrench right here, this setting symbol. It looks like a gear, actually, not a wrench, a gear. Hit this gear right there. And once it says edit list, once you hit that, I want you to hit this create table button. Now, what this will do is it'll give us x's and y's. What did we say our smallest x could be? 0. So I'm going to type 0 here and press enter. It'll just copy right over it. And then I'm going to do 1, 2. I guess I could press the down and start covering over those. 3, 4, 5, 6, 7, 8, 9, and 10. Now, remember how we said the smallest we could sell is 0 cookies? The largest we could sell is 10 cookies. Y'all remember that? Over here, the f of x, we underlined this earlier, the f of x is our profit. Now we know the profit. If we don't sell any cookies, it says the profit is -5. What does that mean? So the one thing I know of in the real world you could have negative on is money. You could have negative money. What does it mean if you have negative money? You lost money or you owe money, one or the other. This situation, it would be that we lost $5. Now, how did we lose $5? Look at the problem. How would it be that if we sold 0 cookies, we lost $5?
Pay for ingredients.
Because we had to pay for supplies, like the ingredients, things like that. Maybe bought some plates to put the cookies on and stuff like that. So that's why we start off with a negative amount and then it gets bigger. Okay, so what are our values? They start at -5. Let's go ahead and write these in. Our range would be, we start at -5. What's our next value? -3.5. What's our next value?
-2.
-2, I agree. And now I'm going to do comma, dot, 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 and we'll do the last two. What are the last two?
8.5.
8.5 and 10. 8.5 and 10. That would be my range for this situation. Technically, you could write them all out, but that's how we did it. Each extra cookie, if you're looking at this, you might notice they're 1.5 apart. And that's because up here, remember how it said it's 150 each? So every single cookie, every extra single cookie you sell makes you an extra $1.50. All right? That was example 1. We got to speed this thing up. We're going to go way too long. So let's try example 2. US Shirts charges $8 per shirt plus a one-time charge of $15 to set up a t-shirt design. The equation right here can be written to model this situation. Now, this problem does not say the word each, but they use something else that means each. What do they say that means each, Lewis, when you get off your desk? Per shirt. In this situation, per shirt means the same thing as each. So what does that mean that's going to be in the problem? Typically your x. Now this problem doesn't use an x. What do they use instead of x? S. So this one, instead of it being an x, it's actually the letter S. So there's our situation. So what is the independent variable? What did we decide? The independent variable is, that means usually the x. What is in place of x? S. And what does S stand for?
For that shirt.
The shirt. Per means the each. So if they say each, they don't usually give you the variable. This one, they used the word per because they wanted you to know we're using the letter S for shirt. That's why I did that. Okay? Hey, David, stay with me. Hey, you need to be writing this down. Danny, you need to be writing this down. I don't know what y'all are doing now. You're getting distracted. Okay, is the independent variable continuous or discrete? Okay, so let's think about this. So shirts. Would you measure shirts or would you count shirts? When you're talking about, we count them because it's countable. Which one's countable? Continuous or discrete? Discrete. Because it's countable, we would say this is discrete. So now, what is the domain? Remember, domain, we say doctor, XY. The domain means X. Well, in this problem, it would mean S. In this problem, it would mean S. The shirts. What's the smallest number of shirts? What's the largest number of shirts? Okay, if we're charging $8 per shirt and a one-time charge of $15 to set up a t-shirt design, this can be written to model a situation. What's the smallest number of shirts you could order? This would be ordering shirts. What's the smallest number of shirts you could order? 0. We would start with 0 again. What's the next smallest amount of shirts you could order? 1. The next smallest number you could order?
2.
The next smallest. Okay, what is, I'm going to go dot, dot, dot. What's the largest number of shirts you could order? Does this one have a largest? So the last one had a largest because they told us she only baked 10 cookies. This one doesn't give us a largest. So if on discrete you don't put an infinity, you just put a dot, 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 and then you do the symbol at the end. That just means you could continue on forever and forever and forever. Danny, what you doing right now? Hey, you need to be doing the math with me. Now, let's talk about range. So how did I find my range last time? We typed this equation in. Let's go to our calculator. Let's type this equation in. I'm going to hit the refresh button up at the top just to make everything disappear. Maybe I shouldn't have done that. It's taken too long. And we're going to type in the equation just like they gave it to us. So I'm going to use the same. I'm not going to change any of the variables. I'm going to do C of S. That's how you would read this. C of S equals 8S plus 15. Now, Danny, if you want to type that in, that's fine. But don't just be distracted again. So type that in. Now that we have this typed in, what did we do last time to find out our domain and range? Yeah, if it were continuous, you could get it from here. But because it's discrete, you hit the edit list, hit this create table. What did we say the smallest was? 0. I went 0, 1, 2, 3, and this could be a 4, but this will give us an idea. So what's the smallest amount of cost we could ever have? 15. So on this one, we would say the range would go 15. And then 23, 31, 39, and then I'm just going to do comma, dot, dot, dot. How much is the range changing by every time? Do y'all know how far apart those numbers are?
8.
8, and that's what the per shirt is. Every extra shirt you sell is $8. All right, so that would be how you do domain and range. The range, I didn't say this, in this problem would be the letter C of S. That would be the Y's. The Y's would be C of S. Okay. I've done 2 examples. I want you to take a look at DOL number 1 here. I'm going to pause. You go ahead and take a look at DOL number 1. Now let's take a look at example 3. It says Nas has $10 and is using an Uber company that charges $2.65 plus $1.05 for each mile driven. Okay, there's a key word in here. What's the key word you see in this problem? Each. Circle the word each. Each always matters. We talked about this earlier. When you see each, what does the each represent? X. Notice the equation below it. You see how this says $1.05 for each? Look down below it. What does it say? What's next to the X? 1.05. That's because at the start here, I'm giving you the equation, but later in the year, I will not give you the equation. I want you to know how it's written. So the $1.05 gets the X, where the $2.65 does not get an X, because it doesn't have the word each. What does plus mean? Add. And see how there's an addition symbol right there? So that's how the equation comes from. This situation can be modeled by this, where X represents miles driven and f of X represents total cost. They're telling me X, remember we circled that up, X represents miles driven, that's the X. F of X, like I said earlier, f of X is always Y. Y is equal to f of X. The f of X is the Y. The total cost, it depends upon the number of miles you drove. All right, you tell me now. Rather than me just do it, you tell me, what is the independent variable in this problem? What is the independent variable? 5, 4, 3, 2, 1. We're on example 3. What's the independent variable? What letter is the independent variable? X. Now, what does X stand for in the problem? Number represents miles driven. That's right. Miles driven. Whoops, got dyslexic. Miles driven. Is the independent variable continuous or discrete? Okay, here's the question. If you were looking at a map to figure out miles you drove, would you count the miles or would you measure on a map? You would measure. This one's measurable. I'm going to write the word here, measurable, above. So we are continuous this time. You would measure the miles that you drove. The cars themselves have what's called an odometer, and it turns. I don't know if you've ever seen this on a car because you don't have driver's license yet, but there's a thing on a car, the little dial that turns, or in digital cars, it just counts up, which is kind of tricky because I use the word count. But the old school, they had a dial that would turn that's measuring the miles that you drive at all times. So what's the domain? Well, if it's measurable, if it's continuous, you always do these symbols around the variable. Domain, Dr. XY. Is domain X or Y? X. So put an X in the middle. What's the smallest number of miles you could ever drive? 0. Now, in this most real world problems start at 0, by the way. In this real world problem, what's the most they could drive? Does it give us a most? If they don't give you a most, just put an infinity. We don't know. Now, more ink, less ink. Here's the question. Could you actually drive exactly 0 miles? Could your car actually go 0 miles? The answer is yes if you never turn it on. So could you actually be equal to 0? Yes. So you put a line underneath. That means you could be equal to it. Different question. Could you actually drive infinite number of miles? Could you ever equal infinity?
No.
No. So this does not get the line underneath. So it would look like that. Okay, now let's go do our range. So go to your calculators. Let's type in this equation. F of x equals $2.65 plus $1.05 x. Now I'm going to show you a different trick. On real world problems, Lewis might remember this because he said something about this. Do you remember where I told you real world problems start? Or which quadrant real world problems are always located in? The answer is they start on the y-axis. So where does this graph start? A real world problem starts right there. But hey, let's say you forgot that. Do you know what you can do? Okay, once you know your domain, you see how we have this domain here? I'm going to show you a trick on Desmos. Everybody watching? On your keyboard, you're going to press Shift, and it's the button right next to P. It looks like this squiggly bracket. Press Shift. It's the key that's just to the right of your letter P. So it's Shift, bracket. Get that squiggly? Now I want you to type in this part. You don't have to type in the infinity to the calculator. Just do. So if you ever have an infinity, don't do the less than infinity. Just do the other part. Do 0, 0. And I'm going to hit the Desmos keyboard to get the less than or equals to x. And when you do that, it cuts off the graph. Looky there. It cuts off the graph and it shows us a picture now. Pretty cool? So you're going to use this squirrely bracket if you want to do that. Okay, so remember, range does lowest to highest, the bottom to the top. Where's the bottom value now that we've cut off the graph? That's called a restriction. Where's the bottom of this graph once we type in this restriction? 2.65. That's our lowest value. 2.65. Remember, you always do these symbols. Now we're doing range. What letter is range? Y. Put a Y in the middle. Go back to your graph. That's the bottom. How tall does this graph go? How high does it go? How high did it go? It keeps going. So what number do you do if it goes on forever? Put an infinity there. Now we have to find out, does 265 have more ink or less ink? Look on the picture. When you click your graph, that dot right there, when you click the dot, is it filled in or not filled in? More ink, less ink? More ink. Guess what we need on our 265 then? What do we need on 265? Less ink. You need it. I'm sorry. Since it was more ink, we need more ink. Okay. Before I wrap this up, I want you to know this. On domain and range, when you have an infinity, you don't actually have to write the infinity. So if we were taking a Desmos test right now, Delta Math, if you were doing Delta Math and it gave you a multiple choice, they don't have to write the infinities. If it's an infinity, you can actually erase that. So what I'm going to do here for their notes, just so you know this, anytime you have an infinity, you can actually write the equation or your answer. You could have just said 0 is less than or equal to x. Why am I saying that? Do you have to write the infinity symbol?
No.
That's the one you don't have to write. You can actually leave, and if you erase the infinity, you have to erase this symbol too. So you could write that this way. You could also say 265 is less than or equal to y. You could write it both ways. Okay, just wanted you to know that. You don't actually have to write down the infinity symbol. All right, let's go to example 4. Crystal has an after-school job at the local hardware store. She makes $12 an hour. She never works more than 20 hours in a week. This situation can be modeled by the function all right here, where h represents the number of hours worked and s of h represents her weekly salary. Okay, in this problem, what letter represents x? Is it just Raven that saw that? What letter represents the x? H. Okay, circle that up. We remember we've been circling that up? H represents the number of hours worked. What represents y? What is in place of y? S of h. That's how you'd read that. S of h. Underline that. So on this problem, y would equal s of h. I'm going to put that at the top. Y would equal s of h, like that. I need you to be working a little bit more before I let you go. So walk me through this. If you want to go, walk me through it. What's the independent variable then?
H.
H, perfect. And what does H stand for? Read the problem. It says H represents what? We'll go to the restroom. You got to get it. H represents what? Number of hours worked. Okay. Okay, so I want you to think on this on measurable versus counted. For time, do we count time or do we measure time with a clock? We count time. So how much time do you have to the end of the school day? Do you count hours or do you measure that off a clock? No, that's not an option. You don't count the clock. Do you count your hours, count your minutes, or do you actually measure it using a tool like a clock? A clock is a measuring tool. What do you do for time? Do we count the time or do we measure the time using a clock? I'm giving you a huge hint. You use a clock, which is a counting device or a measuring device. It's a measuring. You actually measure the time. So time is measurable. So with counting, you don't need a tool. Do any of y'all, well, maybe your fingers you might count with, but other than that, you don't need a tool to count. If you're counting cups, do you need a little tool to count the cups? Or do you just count them with yourself? Just 1, 2, 3, 4, 5, 6. Do you need a tool to count? If I said how many students are in the room, you might use your finger to point, but you don't actually need a tool to count. Now, if you were measuring something, if you needed to measure out flour, you would use a tool. You would use a little scooper that told you how much is there, right? That's what I mean by measuring. You use a tool. A clock is a tool. It's measurable. So this one is continuous. So does that mean we write the domain as a squirrely bracket? No, this is where for domain and range you use these symbols. The less thans with the variable in between. What variable is domain?
So,
X,
X. Oh, in this problem I should actually use the letter H. Because the X is the H. What letter is Y? Or what letters are Y?
S of H.
S of H. That goes here. Okay, so now we're talking about H being the number of hours worked. What's the smallest number of hours you could ever work?
0.
0. Perfect. It's 0. Could you work exactly 0 hours?
Yes.
Yes. How do you work 0 hours?
By not working.
By not working. Okay, so that means it's a line underneath. We can be equal to 0. A line underneath means you can be equal to the number. You could work exactly 0 hours by not working. On this problem, they tell us, what's the maximum number of hours you could ever work? What's the largest number works?
20.
20. Now, could you work exactly 20 hours?
Yeah.
Put a line underneath. So for the range, do y'all want to use your calculators again to help us out? Let's go to our computer, hit the refresh. I guess you could just delete it, but I went ahead and refreshed. I'm going to type in the equation. S of H equals 12H plus 30. I did something last time to make the graph cut off. I typed in a key. Do you remember the key that I typed in?
It's shift vanilla, right?
Shift bracket gives you that same squirrely bracket that you would use if it was discrete. It's that one. Okay, now you type in this symbol, the domain. That's what you type in. Now you'll get an error if you type the letter X this time, so you have to use the letter H. So 0 less than or equal to H, which is less than or equal to 20. And it looks like the graph disappeared. Does anybody know why it looks like the graph disappered?
Because it went off.
No, it's because your y-intercept's at 30. That's the key feature right there. Y-intercept's at 30. Okay, I want to zoom out until I can see the graph. And make sure you zoom way out because there it is. Zoom out quite a few times because you'll see this graph starts and stops somewhere. I knew it was going to start and stop because we typed in a starting value of 0 and an ending value of 20. So I zoomed out until I could see both. Have you zoomed out so you can see both the start and the stop? Okay, we're doing range. What is range?
Range,
Is it left to right, top to bottom, bottom to top? What do we look for range?
top about
Not the top to the bottom. You actually go bottom to top. What's the bottom value? Click on it. What's the bottom value this graph has? Click it. 30. What kind of dot does that have? More ink or less ink?
that's less than
Oh, look, it's
Oh, no,
filled
it's
in.
more.
It's more. So 30 is the smallest amount. Put 30 there. Line underneath. What's the largest amount? So you'll have to click on right there and it'll show you the dot. What type of dot is that? More ink or less ink? At the very top, it's more ink. And what number is it show us at the top? 270. We put 270 there. With more ink. That would be our range. Okay? We have another DOL. Go ahead and pause and try this DOL.